This is where we stopped when we introduced Ohm's law, and we got here just by a simple consideration of resistance and current and what that has to look like as far as proportionality. I'm going to do something similar in this video with resistance. And so let's examine the resistance of a material. And first of all, let me give you a couple of illustrations. Let's say that you are here, right? And you need to get here. This is your goal, is to get over to the other side of this. But you've got people in your way. And their mission is, probably not to tackle you, but they're still in your way, and you're going to have to go around them, or you might have to have interactions with them. You might want to talk to you. They might want to, sell you something. I don't know, whatever. But you need to get all the way over here. Now, the way I've drawn it, you're going to have to take quite a circuitous path, right? You're probably going to maybe have to go here. Well, you really don't like that guy, so you got to go around him over here. But you want to talk to them, and finally you get here, right? So we've seen this in the context of resistance, right? This is a certain amount of resistance. Well, my contention is that if this is your goal, there was quite a lot of resistance to get there, right? But what if this wasn't your goal? What if you only wanted to get here? Well, then there's not a lot of resistance. In other words, you don't have to go through a lot of the interactions and the jostling around to get here as you do here. Of course, if your goal was way on over out of frame and this whole thing was filled with people that you had to interact with and get around, then you would have a lot more resistance. And so my contention is that the resistance of any particular sample of a material, right? And we've got to be careful with that because I'm talking about this particular, hallway. The resistance of this particular hallway has got to be proportional to its length. And when I say this particular hallway, in electricity language, that's the resistance of any particular wire or any particular conductor has got to be proportional to its length. Fair enough. The longer it is, the harder it is to get there. Now, what if instead of this situation, I had this situation? In other words, what if I increased the cross-sectional area of this? And I still had to I'm still here, or you're still here, and you still have to get here. And you still have people in your way. And you might have more people in your way than with the other one. It doesn't really matter here. You're going to have an easier time getting there is my contention. The way I've drawn it, they're more spread out. That may or may not be the case. But at the very least, you have more options. Like, look at what happened here. You hit a wall. You couldn't go any farther. So maybe it's hard to get past this guy, but you don't have a choice. You have to either go down here and you didn't want to talk to him, or you had to squeeze past that. Here, I have more options just because I have a more wide open space, I guess I should say. And so the bigger the area here, the larger the cross-sectional area, the easier it is for me to get to my goal. So the resistance here has got to be proportional to 1 over the area, inversely proportional to the area, right? Fair enough. What can I do with that information? Well, anytime you have a proportionality in mathematics, and we got that proportionality just by thinking, so anytime we got that proportionality, what I then have to do is run some sort of experiment and determine a proportionality constant. So what I've said is that the resistance is proportional to L over A. To make this into an equivalence, I've got to run an experiment and find the proportionality constant. So what I get here is R is equal to the proportionality constant, which I'm going to call rho, times L over A. L over A, physical parameters of my sample of my object, the whatever material I have. Physical parameters. I choose how long it is. I choose the cross-sectional area. This is a physical parameter of the material, right? This is called the resistivity. The resistivity of any material is a function of the microscopic structure, I should say submicroscopic structure, the atomic or molecular structure of that material. So you will find the resistivity of iron is the same in any sample of iron, as long as it's the same kind of iron, right? They're actually, you do stuff with iron. Resistivity of copper is the same for different samples of copper. Resistivity of gold and silver is the same for different samples of gold, same for different samples of silver. But the resistance of a particular instance of those things not only takes the molecular structure into account, it takes the physical parameters of your wire. So you want less resistance, make your wire larger in cross-sectional area or shorter in length, or pick a different material to make your wire out of that has a lower resistivity. Okay, let me just, any good textbook is going to have a chart of resistivities. Let me just give you some samples. Silver, right, has a resistivity of 1.59 times 10 to the negative 8. The units here are, make sure you can still see this, the units here are ohms times meters, right? That's basically there to make you get the right units out of this. 1.59 times 10 to the negative 8 for silver. That's really, really low, right? A low resistivity means that current can flow easily. But that's what you'd expect from a metal, right? You'd expect current to be able to flow easily in a metal. Gold has 2.44 times 10 to the negative 8. Copper has 1.72 times 10 to the negative 8. Things like that. So the lower your resistivity, the better things flows. And so when you look at the better current flows. So when you look at conductors, you should see low resistivity. I want to mention nichrome, which is an alloy of a nickel, iron, and chromium. Nichrome has a resistance of 100 times 10 to the negative 8. So 10 to the negative 8 means this is still pretty small, but notice it's a little less than 100 times more resistive than silver, right? Nichrome, for a conductor, actually has a reasonably high resistance, but it's still small compared to other things. So this is still a conductor. I'll talk about this more in a second. Let me show you an example of an insulator, right? Sulfur has a resistivity of 10 to the 15th. So we've got 23 orders of magnitude in between these two, right? So you would expect insulators to have a really high resistivity because they don't have mobile charge carriers. It's really hard to get charges to flow through to flow through insulators. So we have conductor, really small resistivity, sulfur, really high, or insulators, I should say, really high resistivity. Now, why did I talk about nichrome? Well, I want to talk about the results of, or the noticeable side effects, I guess you can say, of resistance. So, you probably don't need to know what's going to happen when I put my hands together and do this, right? What's happening to my hands? They're getting warm. Why are they getting warm? Friction. So what's happening on the atomic level is I've got interactions between these large structures like atoms and molecules and these little charge carriers. Now, this is not friction, right? There's no friction at the microscopic level, but there's something analogous to friction. These interactions are collisions, right? They involve, and they're perfectly elastic collisions, if you remember that from Physics 1. Perfectly elastic collisions conserve energy, but that does not mean the energy doesn't move around. And so there's constant exchange of energy between the charge carriers and the larger structures. What that means is, and notice the charge carriers you can think of as deriving energy from the electric field. That's a terrible way to say it. There's an electric field inside this wire, which is set up by a voltage across the ends of the wire. The voltage times this charge is going to give you some sort of potential energy. And so in some sense, there is a way for the charge carrier to replenish its energy from the potential, but it gives some of that energy all the time to these other structures, right? It's giving up energy to these atoms and molecules. It's getting more energy from the potential, so it continues to move, no big deal. But some of that energy is spent or wasted, if you would like to say that in the language of thermodynamics, given over to these atomic or molecular structures. Well, what does that mean? If these things gain energy, that means they're vibrating, right? So that means their kinetic energy of vibration increases. If you've ever studied any thermodynamics, this means they heat up. They get hot, right? They get hot. What gets hot? These larger atomic and molecular structures. They're receiving an almost constant input of energy from the charge carriers, which are colliding with them. And so they heat up, they get hot. Now, if you've ever charged your computer or used your computer for a lot of data processing, like streaming movies or uploading videos to YouTube, and it happens to be sitting on your lap when you do this, there's probably not any surprise about that. It gets hot. If you've ever touched your phone, if it's not in a case, if you've ever touched your phone after you've been charging it, it's hot, right? This is what happens when a lot of electricity flows. Things heat up. So why did I mention nichrome? Why did I talk about that? Nichrome is a good example because we all know what it is, whether or not we know what it is or not. Go toast a piece of bread. Look inside your toaster, and what do you see? You see glowing wires that are kind of arranged. I'm assuming I'm inside the toaster looking at it. They're kind of arranged like this. What that is probably, I don't know your toaster specifically, but if it's like most other toasters, this is a wire of nichrome. Now, nichrome had a pretty high resistivity, right? Which means it resists the flow of current. It's still a conductor. Current can flow. But what happens, that high resistivity results in a high resistance of this particular wire, which results in this particular wire getting pretty hot. So hot, in fact, that it glows orange. Well, that's a good thing in this case because we need it to toast our bread and make it delicious. You know, in some situations you might not want that, but it's just, you can't avoid it. It's a byproduct of current flowing through this wire. The resistivity of nichrome results in a particular resistance of this wire, which makes it hot, which ends up toasting your bread. If you've ever looked at the filament of an old school incandescent light bulb, I realize that most everybody uses compact fluorescence these days, right? So here's my old school light bulb. It's got, you find these most in decorative light bulbs these days, in Edison light bulbs they call them. It's got a little bitty filament. That filament is an alloy of tungsten. Why does the light glow? Because you run a current through this little bitty filament. And this little bitty filament, number one, the cross-sectional area is tiny, so the resistance kind of goes up through the roof. Notice also it's coiled, so it's a lot longer than you think it should be for being in this space. So both of those things contribute to the resistance, plus it's got a high resistivity. So what happens? It heats up because of the flow of electricity and because of the resistance. When it heats up, of course, it glows. And we want that, right? But if you've ever touched an incandescent light bulb, right, it also is hot, right? If you've ever had an easy bake oven like my sister had, right? If you don't know what that is, it's a little bitty box that they sold as toys to children a long time ago. It's got a light bulb inside it. You can make cookie dough. You put the cookie dough inside it and turn on the light, and like 6 hours later, you might have a cookie that's kind of halfway done. It doesn't cook very fast because they don't put out a lot of heat, but they do put out some heat. One of the things I like to do in my spare time is bake bread. It's kind of a passion of mine. And the bread has to rise for a large amount of time in a warm environment. The bread I make usually takes an 8-hour rise in a warm environment. So what do? I put it in my oven. I don't turn my oven on, but I turn my oven light on. And that produces enough heat to activate the yeast, right? So the whole point of this is all of that happens because current is flowing. This wire has a high resistance, and so it heats up. It heats up so much, in fact, that it glows. To toast bread, or to bake a cookie, or to see, to do your homework, whatever it takes. The resistance is what makes these things actually work. The resistivity, of course, is the parameter of the material, and different materials have different resistivities. Of course, this leads to easy problems to answer. If you're asked for the resistance of a particular length of wire of a particular substance, and that wire has a particular cross-sectional area, it's easy to find the resistance of that if you know all these parameters. This is something you would probably look up on a chart. These are two things you measure, and so you can find your resistance that way. Now, any wire has resistance. Of course, wires are made of conducting materials. Conducting materials have some sort of resistance. But there are also electronic circuits that we, or electronic components that we put into circuits to create resistance. As it turns out, very often we want to control the flow of electricity in very precise ways, and so one of the ways we do that is by putting different resistances into a circuit. And so let's put another battery here and connect this thing to some wires. And the symbol for a resistor is that. It's just a jagged, squiggly line, right? So here's my voltage source, here's my resistor. Now, in this course, and in pretty much every E&M course you're ever going to take, what we're going to do is assume that our wires are resistance-less. That is absolutely not true. But we're going to let the resistance of the wires either be negligible, or we're going to wrap it up into a resistive component. So when I draw this could be something that I go to an electronic store and I buy a little component and I put it in here to create more resistance. Or this could just be symbolic of the resistance of these wires, and I'm considering this portion then and this portion to not have any resistance. It's just a simplification we make. It doesn't really matter which one it is. We can characterize the circuits the same way. So when you see this symbol, that is the symbol for a resistor, which is the electronic component that creates more resistance. And so just as a reminder of our graphical terminology so far, that's a battery. It will either have a V. Very soon we're going to start putting an E, a script E for EMF there. We'll talk about that in a few sections. But this is the symbol for a battery. We have the symbol for a capacitor, and now we have the symbol for a resistor. Okay, all right. For those of you who are making a glossary.